to our online NPTEL course Environmental Chemistry and Microbiology. This course will be taught by Professor Sudha Goel and myself, Professor Anjali Pal. We are both from Department of Civil Engineering, IIT Kharagpur. We have divided this course into two parts. The first part, environmental chemistry, will be covered by me, and the second part, environmental microbiology, will be taught by Professor Sudha Goel. Now, this is the module 2 and this is my 10th lecture on chemical equilibrium. The topics here I have covered, it is different problems as well as observations that I wanted to combine here, and all are on the chemical equilibrium concept. So, I hope you will like it. The first one is the copper detection. You know that almost all metals are white in color, but the copper you see that it is brownish color, and gold you see that it is yellow color. Now, when copper you keep it in air, then it slowly goes to copper 2 plus. You see some blackish tint in the surface of the copper metal, that is nothing but copper oxide, and then copper 2 plus we know that it is blue in color. Now, copper produces copper sulphate upon reaction with dilute H2SO4 in air. This is a slow conversion. So, copper if you put in copper sulphate in H2SO4, dilute H2SO4, then it will in air, under air, then it will slowly produce the copper sulphate solution, which is blue in color and which is known as blue vitriol. On the other hand, what we call the sulphuric acid, it is the oil of vitriol. Now, we know that from acid base chapter I told you that copper sulphate is a normal salt. It is neither an acid salt or a basic salt, it is a normal salt, and it forms a complex salt with dilute ammonia. So, if you take some copper ion, say copper sulphate, then you put the ammonia solution there, then it will depending on the concentration of ammonia, different reaction occurs. What is happening? Introduction of dilute ammonia to blue copper sulphate solution. If you take in a test tube some copper sulphate solution and if you add ammonia solution there, if it is little amount, ammonia is low amount or low concentration, then what will happen? Then it will form a basic salt. This is nothing but copper sulphate, copper hydroxide, okay, and it is a blue white precipitate. Okay. You will see a blue white precipitate formed in the test tube. Now, if you increase the concentration of ammonia, then what will happen? Will finally this precipitate goes to solution. How? Due to the formation of copper amine complex CuNH3 whole 4 2 plus, this is the ion, and the corresponding salt is CuNH3 whole 4 sulphate, because sulphate ion is there. So, it will form this salt. So, you have increased the ammonia, then this precipitate will go into solution and it will form this one. This gives a transparent blue solution, and this is a taste of copper 2 plus ion. This is also shown here as the reaction. Copper dilute H2SO4 gives copper sulphate solution which is blue, then copper sulphate with aqueous ammonia gives this basic salt which is a blue white precipitate, is a basic salt, and then you increase the ammonia concentration, higher concentration, then it will form the complex salt. So, this is a very good taste of copper ion. Now, similar thing can happen for silver also, and it is also a silver ion detection. What is happening? You take silver nitrate solution in a test tube, okay. It is colorless. We all know that silver nitrate solution is colorless. Now, to this NaCl solution if you add, then what will happen? Because this is a source of chloride. So, chloride will react with silver nitrate to form a white precipitate. It is called curdy white because it is like a curd that we eat. The precipitate will be like this only, and then now aqueous ammonia is added to the precipitate. Then what will happen? So, if you add the ammonia solution in the silver chloride precipitate, then what will happen? Then the precipitate will dissolve. Why it will dissolve? Because it will form some amine complex, silver amine complex, that I already showed you. This is because of the formation of silver amine complex. Now, what will happen? If you add again the silver, if you again add there in the silver amine complex, if you again add the HCl, what will happen? Again HCl is added to the solution, then what will happen? The white precipitate reappears due to the formation of silver chloride again. This I have already explained, but it can be you can do the experiment in the laboratory, because all chemicals that is used here is available in the laboratory. So, what you have learnt in the previous lecture, that formation of silver amine complex, then it is breaking to silver chloride again, you can do it easily in the laboratory. Here in the reaction also the shown silver nitrate with chloride, it gives silver chloride curdy white precipitate. You can see the precipitate, then you add ammonia solution, it will form, it will solubilize, then it will form the silver amine complex. After that you add some HCl to it, and then you will get back your silver chloride as a curdy white precipitate. This is a very good demonstration, and indeed it is a method for silver plus detection also. Now, very interesting demonstration of green chemistry. I will ask you some questions here. So, please listen carefully. Say for example, silver nitrate, which you know that it is a very most common silver salt, and it is used for chloride ion detection. Then one can easily observe a curdy white precipitate formed from silver nitrate and HCl, that I have already told you, okay. And this is a test for chloride ion, and it is also we use this reaction in the chloride ion determination also. We all know Morse method, okay. In turn, it is a method for silver ion also. Now, this the property of silver ion is silver chloride is that it is soluble in concentrated HCl, okay. It is soluble in concentrated HCl, please remember this. Now, we do another experiment. What we do? We take a test tube, okay. This is a test for sulphate. So, similarly, the test for sulphate ion is performed with the water soluble barium chloride. We all know how we do. Barium chloride produces white crystalline barium sulphate precipitate with sulphate ion in water. Barium sulphate is insoluble. You have already learned from the solubility product in the earlier lectures, okay. But the property is different. Here both are white precipitate, silver chloride and barium sulphate. But a silver chloride is curdy white precipitate which sticks to the surface of the test tube, but barium sulphate is crystalline precipitate which you can see it, okay. Now, barium sulphate is insoluble in all acids and alkalis. So, see the difference in the properties. So, if I ask you that how can you say both are white precipitates, but how can you say which one is silver chloride and which one is barium sulphate? Then you can easily tell that, okay, in one precipitate if I add HCl it will dissolve, in another it will not dissolve. So, which one dissolves is AgCl and which does not dissolve is barium sulphate. This is a test by adding some chemicals. This is not green chemistry approach. You know that we have to do it without using some reagent, okay, or without using too many things. If we can do something, then it is a green approach, okay. So, my question is coming now. Now, say two test tubes I have given, in one case it is having the silver chloride, another case it is having another test tube it is having barium sulphate, okay. One containing barium sulphate precipitate, in water and another silver chloride in water. Both are white precipitate, you are not given any HCl to test. So, how you can test? Without putting any reagent, how can you tell something is AgCl and something is barium sulphate? This, if you can do that, then it is a green chemistry approach, green chemistry protocol. Can you do that? This is my question, can you do that? Yes, you can. You can think of classical photography, okay. Classical, now everybody is using the digital camera. So, now we are almost forgetting the classical photography where silver salts are used, okay, where silver salts are used. If you hold both the test tubes in sunlight, in the classical photography also we do the same thing, okay. We expose the silver salt with light, okay, and then it becomes colored in black, silver chloride it will become black. Now, if you hold both the test tubes in sunlight for a small period of time, then in one PPT, one precipitate will turn black and the other will remain white. Which one will turn black and which one will remain the same? So, silver chloride which will turn black. Why? Because with photon you know that this will decompose to form the silver, okay, and silver is black, and barium sulphate will not react with the photon. So, it will remain the same. It is a very simple experiment to understand, okay, and this is a green chemistry protocol, green chemistry approach, okay. Now, I will tell you another very simple experiment, okay, that we use in chloride determination, okay, where we use the potassium chromate as the indicator, okay, for chloride determination. Now, can you reverse the charge of a colloid? You all know that colloids are stable particles, okay, because of their stability. How they become stable? Because mostly some ions are adsorbed onto it, okay, either positive or negative, but usually negative ions are adsorbed on it and they repel each other and they become stabilized, okay. So, I will tell you about two experiments, okay. Silver nitrate solution you take, okay, it is very common. In a test tube you take silver nitrate solution and you add excess NaCl to it, okay. When you add excess NaCl, so some part of silver plus will form the silver chloride as the precipitate and it is Cardi white precipitate, you all know, and then because you have added excess sodium chloride, so chloride ion will be in excess, okay, and in the solution there are many ions, okay. What is there? There is some sodium ions that is coming from here, sodium chloride. There is the chloride ion which is because you have used excess, so some chloride ion will remain, and there will be some nitrate ion which is coming from silver nitrate. Now, who will adsorb onto the silver chloride? Because I said that the colloids are always stabilized by charge, okay. So, who will adsorb onto it? It has the choice, different choice. So, who will? Actually, you see that it will always prefer to have some ion which is family member. What is that? Here in his family who is there? Silver is there and chlorine is there. So, either silver ion or chloride ion will be deposited. Deposited means adsorbed onto it. There is no silver ion because you have taken less amount of silver nitrate compared to sodium chloride. So, all silver ion is precipitated as silver chloride, but you have excess chloride. So, neither nitrate will adsorb onto it nor sodium plus, but chloride ion will be, because it is a family member of this one. So, it will adsorb and it will form a negatively charged colloid. Okay. It is a colloid, but it is stabilized by negative charge adsorption. Okay. Now, just do the reverse thing. Okay. You take silver nitrate in a solution and then you add sodium chloride in trace. You add small amount of sodium chloride. Okay. Now, still here you will get the silver chloride as the precipitate, okay. But here you have added NaCl trace amount. So, silver nitrate will be remaining as excess. So, silver plus will be in excess, nitrate will come from here, and you do not have any silver here because all silver has been you do not have any chloride ion here, because you have added sodium chloride in trace amount. So, all chloride will be will be converted to silver chloride, but you have this choice. So, who will adsorb onto it? Here you see that silver is the family member. So, silver plus will be, although it is a plus positive charge, but still it will be adsorbed onto it. So, now you will get the positively charged colloid, positively charged colloid, silver same silver chloride in both cases, but in this case because chloride is in excess. So, it will be stabilized by chloride ion, and in this case because silver is in excess. So, it will be stabilized by silver ion. Now, once it is obtained, then what will happen here? If you remember the chloride ion determination, then you remember that we use the potassium chromate as the indicator, which is yellow in color. But once this is formed, because after the titration is over with sodium chloride taken in the conical flask, you have added excess of silver nitrate. So, now you get this type of colloid, silver plus stabilized colloid. Now, it is silver plus. So, it will immediately attract the chromate ion, and then it will be for charge neutralization, because this chromate ion will be adsorbed here, it is attracted by silver plus, and then you will see the color brick red color at the end point. Okay. Silver chromate, this is silver chromate color, brick red color in the end point, at the end point. So, this is a very interesting observation, interesting experiment that you can easily perform in the laboratory. Now comes the hardness determination. We always do the hardness determination by EDTA titration, ethylene diamine tetraacetic acid. How we all know that hardness is caused by whom? By multivalent cations. Although many people think that it is caused by calcium ion or magnesium ion, but actually it can be caused by other ions also which are multivalent, like iron, ferrous, or maybe manganese, or even maybe strontium, Sr2 plus, barium 2 plus, anything, but usually strontium, barium, they do not occur in nature. But this iron and manganese always occurs in nature. In many states we see that manganese 2 plus is present in the groundwater, same is true for iron. In many places you see that groundwater contains iron in huge quantity. Okay. Now, the hard waters are those waters that require considerable amount of soap to produce lather. This is the definition of hard water. And hard water produces scales. Why? Because in hot water pipes, heaters, boilers, because of the formation of calcium salt deposited. Okay. Now, calcium or magnesium salt. Now, when we determine the hardness, that is we determine the calcium magnesium ions, then we use the indicator which is called aerochrome black tea, EBT. Okay. And we do the titration with the disodium salt of EDTA. Many people say that we do the titration with EDTA, but it is not true, because EDTA is not soluble. Okay. It is a weak acid. We now all know that weak acid are weak electrolyte. Okay. So, they do not get solubilized in water. That is why we use disodium salt or tetrasodium salt of EDTA. Okay. Now, what is happening? We take the hard water in the conical flask, then we add EBT a few drops, and then EBT color is blue, actual original color of EBT is blue, but because there is some calcium magnesium ions present in the water, and also we maintain the pH in alkaline range by ammonium hydroxide ammonium chloride buffer, that I already told you in the that buffers I have already explained in the acid base chapter. Okay. But here we use that buffer anyway. So, after that we start our titration with EDTA. Now, what color initially what color we see is the color of the complex formed between a few ions of calcium magnesium ions with the EBT. That means, EBT has blue color, but when it complexes with calcium magnesium ions, then it becomes rose red color. So, initially in the start we see the rose red color. We start with EDTA. Now, what will happen? Titration is started with EDTA. EDTA is a very good complexing agent. So, it complexes with the free calcium magnesium ions present in the conical flask, that is sample water. Now, slowly EDTA concentration is increased, all the calcium magnesium ions get complexed with the EDTA by then while reaching the end point. Now, end point is reached. So, what will happen? All the calcium magnesium ions will be consumed by the EDTA through the complex formation. Now, what will happen? Now, the EDTA 2-3 drops extra will attack the complex formed between areochrome black tea and the calcium magnesium ions, that is rose red color I told you. So, it will attack, the EDTA will attack that complex also, and then what will happen? Then that calcium magnesium ions will be captured by the EDTA, and then the areochrome black tea will remain free, and then you will get back the dye color, that is the blue color at the end point. Now, the question is that why EDTA finally it is breaking this complex EBT calcium magnesium ion complex, that is the question. And here another thing is very important to mention, that in this complex metal ion EDTA complex, the stoichiometry is 1:1. Okay. Now, this is for calculation, we need this thing. Okay. Anyway, so now my question is why it is breaking this complex, that is that metal ion indicator complex, because this is breaking that complex because metal EDTA complex is much more stable. So, who is more stable, that will be formed. Okay. And if you compare the K value, that is the that equilibrium constant, or you can tell in the case of complex you can tell that stability constant or formation constant. If you compare, then you will see that K metal EDTA complex is to K metal indicator complex is very large, it is more than 10,000, you see 10 to the power 4, that means it is very stable. So, EDTA will break this complex areochrome black tea metal that complex formed between metal ion and indicator, and then finally indicator will be free, that is showing its original indicator color, and the metal will be captured by the EDTA. Okay. So, this is a very important part, okay, and that has been used for the calcium ion, that is not calcium ion, actually hardness determination. Okay. So, formation complex is such an important thing in equilibrium, chemical equilibrium. Okay. Now, electroplating, this is another example which is very much effective, is very much useful when you do this equilibrium I will tell you later, but actually in the electroplating industry this type of equilibrium is used for electroplating some metal utensils or metal something with silver or gold or copper or nickel. So, why we do the plating? Because to protect the maybe iron or brass, we want to protect it, or we want to make it beautiful by gold plating or silver plating. So, we use this. Now, the important part I will tell you, in case of metal plating, the electroplating bath that consists of a solution of the salt of the plating metal by which you will plate, okay. Say for example, silver or gold like that. So, that salt is there in the metal, in the bath, electroplating bath, and we use a cathode. A cathode is used. What is the cathode? It is the article to be plated on which you want to plate the silver or gold, okay. And the anode is the plating metal. That means, if you want to make it with silver plating, then or gold plating, then anode will be that metal, okay. And then in the silver plating solution, argento cyanide, argento means silver, argento cyanide is electrolyzed, okay. It is not silver nitrate, it is argento cyanide. This one AgCN2 potassium, like this potassium argento cyanide, okay. this is used. The anode is a plate of pure silver, okay, because you want to do silver plating, and cathode is the article to be plated. Okay. The electrolytic bath is prepared by adding excess KCN to AgNO3 solution. So, when you add KCN, excess CN to AgNO3, it will definitely form the argentocyanide, this one. Okay. Now, so in your electroplating bath, you have argentocyanide which will be electrolyzed. As the cathode, you are using the something which you want to electroplate, and the anode you will use, in the anode you will use the silver. Okay. Now, if silver nitrate alone is used, what will happen? Why we are using this one? That is the main topic here. Okay. The anion AgCN2 minus, it is a complex, you can see here it is a cyano complex of silver, is only slightly dissociated. It is not completely dissociated like silver nitrate. Silver nitrate is a strong electrolyte, it will 100% dissociate, okay, but here it is slightly dissociated, and once it is slightly dissociated, so it will be deposited on the electrode to form a very thin uniform film. So, it will go on in a very slow process, okay, and then it will form a very thin film of silver, uniform thin film of silver. If you use silver nitrate in the as the electrolyte, then you will get a coarse spongy silver deposit, okay, because silver nitrate is a strong electrolyte, and it will the electrolysis will go on fast, and you will get a spongy silver deposit. Okay. This is the beauty of this electroplating with silver. The cyanide ion discharges on the silver, then what will happen? In the anode the silver the cyanide ion will be discharged to form silver cyanide. This silver cyanide will again dissolve in the KCN that you have taken in the bath. So, to form the potassium argentocyanide. The reaction is shown here. Silver nitrate you have taken in the bath, silver nitrate and excess KCN, which will form this complex. Okay. After that, this complex will ionize to form this one. Okay. This will ionize, and then this complex of silver, cyano complex of silver will again ionize in a slow manner. Okay. That is why it is written here that is only slightly dissociated. It is slightly dissociated, it is in equilibrium, it is slightly dissociated to produce silver plus, which will be deposited in the cathode to make the silver plating. But if you use silver nitrate, then this type of thin film will not be produced, instead you will get a spongy silver deposit, which is not wanted. Okay. So, this is a very good example of the complex formation and its application in electroplating. The same you can do with gold also, gold cyano complex you can form, okay, and to prepare to make some gold plating on something. Okay. This is a very nice example. So, from the chemical equilibrium chapter or chemical equilibrium the discussion on chemical equilibrium, we have learnt many things. So, we learnt how to apply chemical equilibrium concept to understand the solubilization and precipitation phenomena in a better way, and we can solve many environmental problems. And the concept is also very useful to understand the analytical methods for detection and determination of many analytes. Chemical equilibrium is a very important chapter. We must get the proper idea, and we must know how to form the equilibrium expressions, what is the impact, and so you can learn from different books, but these books I have taken many examples from these two books. You can read these two books to get even better idea. Thank you so much.